Hello, this is Len McCallum, and I'm just doing the video presentation for Chapter 5, which is, of course, dynamic routing. So it is, some of it at least, is a bit of a review of what was done in Semester 2, but it does certainly go into more depth than routing and switching essentials. Okay, so first we're going to look at dynamic routing protocols in general, and then we're going to look at specific types, and so then we'll look at distance vector dynamic routing protocols, and then we'll look at link state ones as well, and we'll look at the differences between the two. Okay, so dynamic routing protocols. So the reason we have them is a good automated way of discovering remote networks. It maintains up-to-date routing information in the routing tables. It's able to choose the best path to a destination based on typically a metric, and it's also able to find an alternate best path if the primary path has failed for whatever reason. Now, on the diagram there, it actually sort of shows the ways we can classify routing protocols, and so, of course, as I said, overall they're dynamic routing protocols. Then there are interior and exterior gateway protocols. So interior is within an organisation, exterior is between organisations. Now, basically, there's only one type of exterior gateway protocol because there's only one run on the internet. It's called BGP, Border Gateway Protocol. And so, yeah, that's what is used by ISPs and other major companies to route packets over the internet. When it comes to interior gateway protocols, as the previous slide mentioned, there's two ways we can define those, as either being distance vector, which of course means it knows how far away the destination is and in what direction, and that's all it knows basically. And then there's of course link state routing protocols, which knows the status of every link in their domain. Of course, the types of distance vector routing protocols, they're RIP and IGRP were the original two major ones. RIP, of course, is Routing Information Protocol. IGRP is Interior Gateway Routing Protocol. Now, that's Cisco proprietary, the IGRP. Now, RIP version 1 came out a very long time ago, and when people found flaws, well, not flaws, but just inabilities of the routing protocol, they actually released an updated version called RIP version 2, and that is much improved. And of course, the same thing happened with IGRP. And so EIGRP is Enhanced Interior Gateway Routing Protocol. When it comes to link state routing protocols, OSPF, which is Open Shortest Path First, is the most common one, and another one which is called ISIS or ISIS, which means Intermediate System to Intermediate System, which of course is router to router. And so I've pretty much already explained the differences there. And so, as I said, distance vector means it knows how far away the destination network and in what direction. Some people call it routing by rumor because that's basically the only information they know. And so, and of course, as with most routing protocols, they use a metric to make a decision on what is the, say it's much the same as if you're going to drive from Adelaide to Melbourne, you would choose the shortest path, you wouldn't go via Perth. And so routing protocols try to do much the same thing. They try to choose the shortest path as being the best one. How you measure that shortest path is by a metric of either hop count or bandwidth or cost, which normally goes back to bandwidth anyway. And so, of course, the distance is what's the next hop towards that destination when it comes to vector. Okay, so link state routing protocols actually have a database for every link in their domain, as it were. And so they know the speed of that link, they know what routers are connected to that link, and they know the status of that link. And so from that, once they have all of the information on on the network, they can then select the best path towards a destination network. Link state routing protocols do not use periodic updates. So RIP, for example, does a broadcast its routing table every 30 seconds. Link state routing protocols do not do that. They exchange link state advertisements when either they start up or when the information changes, but basically apart from that there's no information changed other than just hello packets, so they can sort of keep track of one another, so they know that everything's still working. So another way we can classify routing protocols is if they're classful or classless. Basically, classful is the old way of doing it, and so RIP version 1 and IGRP you saw on one of those earlier slides were classful routing protocols, which basically means because they don't send subnet mask information in their updates, the receiving routers need to make assumptions about the subnet masks of those networks that have been advertised, and so it gives you less flexibility when it comes to designing an addressing scheme for your network. While classless routing protocols, because the subnet mask information is sent with the updates, the routers have more information. They don't have to make those assumptions, so it actually gives you a lot more flexibility in the addressing. And so, if you remember VLSM from the first Cisco course, variable length subnet masking, you need to have a classless routing protocol to be able to do that. And so RIP version 2, EIGRP, OSPF and ISIS are all classless routing protocols, and so as I said, because they send the subnet mask information, no assumptions need to be made. Gives you a lot more flexibility. As you can see, there are 30-bit masks on those serial links and 24-bit masks on the LANs, and so it's a lot more flexible. IPv6, there's no such thing as address classes really, apart from there are ranges that are used for different purposes, but when it comes to normal unicast addressing, there's no class system. It's a classless society. So comparing different routing protocols, so speed of convergence is how long does it take for a network change to be propagated through a network. And so scalability means how large can you build a network with this routing protocol. VLSM is just whether it's supported or not. Resource usage is how much CPU and network bandwidth is used for those protocols. And the last item there is how easy is it to implement these routing protocols. So when it comes to speed of convergence, most of your distance vector routing protocols are pretty slow. EIGRP is certainly fast. When it comes to scalability for the size of the network, they say the old ones are all small networks. IGRP I would have personally said was medium, but its speed of convergence sort of did hamper that a bit. It's only the more recent ones that, of course, that support VLSM. Your distance vector routing protocols don't use a great deal of resources. Now, EIGRP, they've classified it as distance vector, but it also does some things a bit like a link state routing protocol as well. It's hence the enhanced part of its name. And so it does use some more resources, but it's that extra functionality that increases the speed of convergence in EIGRP. So it's a bit of give and take as per often. And then when it comes to implementation, RIP is pretty damn simple to do. EIGRP, you could do it as easily if you want, but it's got many options that you could get very complex with. So when it comes to link state routing protocols, because they know all the information in the network, they do converge quickly. They are very scalable for networks. They can actually divide into separate domains within that, and that makes convergence much faster on very large networks. Yes, they do support VLSM, but they do use high resources, and so those databases that they use, and if there are major changes in the network, those link state advertisements can take a lot of bandwidth as well. and they can get quite complex. I'm to say if you do single area OSPF, it's not too bad. It's still a little more complex than the others, but yeah, once you start talking about multi-area OSPF, it's quite complex. Okay, so metrics I have mentioned earlier. So a metric is a measurable value that is assigned by the routing protocol to different routes based on the usefulness of that route, so or desirability of that route, basically. The lower the cost, the better the route. And so routing metrics are used to determine the overall cost of a path from source to destination. And as I said, the lower the cost, the better. You know, driving directly from Adelaide to Melbourne, what is it, about 800 kilometres? You know, if you did it via Perth, it'd be about 5,000 kilometres. So, you know, which would you prefer? Now, different routing protocols use different metrics. Rarely are they interchangeable at all, and they're quite different. And so RIP uses a very simple one of hop count, which is how many routers would it need to go through, while OSPF uses, it calls its metric cost, but it's actually just calculated by bandwidth, and EIGRP uses a combination of bandwidth and delay by default, but you can also use load and reliability if you feel the need. Now, looking at the diagram here, you can see that you've got PC1 and PC2 hanging off of routers 1 and 2. But if you look at the link directly between them, that's 56K, which is, you know, dial-up speed, snail's pace for these days. T1 is 1.544 megabits a second, which is these days not particularly rapid, but a lot better than 56K. And so if RIP were to make a decision which was the best route, it would actually use the 56K route because there's only 2 routers in that loop, while this one has 3. And so hop count is the metric they use, so RIP would use that 56K route, while the other routing protocols would actually send it via router 3, and you would probably get faster performance out of that. And so hop count, while as simple, is not necessarily optimal. Okay, so specifically about distance vector routing protocols. And so all dynamic routing protocols send and receive messages on their interfaces. With distance vector, they typically broadcast their routing table to their neighbours, and of course their neighbours will advertise their routing tables to them. And so that's how the routers learn information about remote networks. When a router detects a topology change, the routing protocol can advertise this change to the other routers. And so that's that automated updating we were talking about earlier. And so after a router boots successfully, it applies the save configuration. Then the router initially discovers its own directly connected network. So we've all done this. We've configured a router with IP addresses on all the interfaces. Well, that's initially the only entries in the routing table on a router. And so, as you can see here, the router 1 has 2 networks, router 2 the same, and router 3 the same. Of course, there's 1, 2, 3, 4 networks, and so the routers don't have all of the information. So a host on network 10.1.0.0 would not be able to communicate with a host on 10.4.0.0 because router 1 doesn't know how to find that network, and vice versa. If a routing protocol is configured, the router exchanges routing updates to learn about any remote net routes. And so this takes time, especially with the distance vector routing protocol. So as you can see here, routers 2 and 3 have exchanged information. Router 2 has sent its information to router 3 has sent its information to router 2. And so router 2 knows about all the networks. Router 2 has also sent its initial information to router 1. And so from there, they're starting to build their information, but until all 3 routers know about all 4 networks, things aren't going to work. And so it builds slowly, and then after an amount of time, a couple of cycles at least, depending on how large the network is, then the routers will then know about all of the networks. Now, working toward convergence, the routers exchange the next round of periodic updates. Distance vector routing protocols use split horizon to avoid loops. Now, split horizon prevents information being sent out the same interface it was received from. So router 1, of course, learnt about networks 10.3 and 10.4 from router 2. Why would router 1 tell that router about those networks? Because that's the one it learnt it from, you know. And so if it did do that, and then networks 3 or 4 went down, well, router 2 would think, oh, well, router 1 knows how to find that network now. That's an alternate route. And so you'd actually probably end up with packets bouncing between the two routers until their TTL expired, which is not great. And so that's why split horizon is a way to stop routing loops. So convergence, of course, as I said, is when all the routers agree on how the network looks, and so all routers have routes to all the networks. As you see, we must be talking about RIP because we're using hop count as the metric. Convergent time is the time it takes for that to happen, and of course, as we looked at that table, that's one way that you can compare routing protocols. So distance vector routing protocols share updates between neighbors. Routers using distance vector routing are not aware of the network topology. Some distance vector routing protocols send periodic updates. RIP version 1 broadcasts its updates to the broadcast address. Your more modern routing protocols actually multicast, and so only those hosts interested will actually see those frames arriving. EIGRP can use a unicast message to reach a specific neighbor router, and it only sends updates when needed, not periodically. So RIP does its updates every 30 seconds, as I said earlier. EIGRP, as I said, plays a little bit like a link state routing protocol and only does periodic updates. So the distance vector algorithm defines the following process: mechanism for sending and receiving routing information, the mechanism for calculating the best paths and installing routes in the routing table, and a mechanism for detecting and reacting to topology changes. RIP uses the Bellman-Ford algorithm as its routing protocol. This line I don't agree with, but anyway, EIGRP uses the dual diffusing update algorithm. As far as I was aware, IGRP always used the Bellman-Ford, but anyway, just with different parameters. But so, what's good about routing RIP? So it's easy to configure. Routing updates are broadcast every 30 seconds. Metric is the hop count, and it actually has a 15 hop limit. That's on all versions of RIP. Now, RIP version 2 is for IP version 4, and so that sends the subnet mask information with the updates, and so it supports VLSM Insider or is classless. It increases in efficiency because it uses multicasting instead of broadcasting. You can also do manual route summarization, and you can actually do authentication to make it more secure. RIP-NG is designed to work with IPv6. It's other than the addressing supports, it's identical to RIP version 2. 15 hop is the limit, and the administrative distance, which is a way that the routers compare routing protocols, is 120. The higher the number, the less reliable it is deemed to be, and 120 is one of the higher numbers. So they don't deem it to be particularly reliable. So the table here compares them, pretty much reiterates what was said in the text. Okay, so EIGRP was released in 1992, and so it was basically version 2 of IGRP, and so it has bounded triggered updates, and so that means it sends only changes to the updates and only to the routers that need it when they need it. They have a hello keep alive mechanism, so they send hello packets to maintain their relationships with the neighbouring routers or adjacencies. They have a topology database or table, and so again, very much like a link state routing protocol. Rapid convergence because it actually has alternate routes to destinations already set up and ready to roll, as long as they meet certain conditions. And EIGRP was actually written to support many layer 3 protocols. Now, these days, we can probably only think of two that are in use, IPv4 and IPv6. But if you think back 15 to 20 or more years ago, there was actually a lot of other protocols out there. So there was IPX, there was AppleTalk, there was DECnet, there was a whole pile of other layer 3 routed protocols, and so they actually did modules for many of those. And so you could basically use a plug-in module and run EIGRP using those. So it was a modular setup, so it's quite well designed. All right, so link state dynamic routing. And so they all use the shortest path first algorithm, which was actually designed by the mathematician Dijkstra. I think he was 50s or maybe 60s mathematician from Holland, as you can tell by his name. And so it was just a theoretical algorithm that he developed as a way of routing stuff. It wasn't necessarily data traffic, but it was an efficient an algorithm that could figure out an efficient way to route things. And so when the limitations of RIP became obvious, someone thought, well, when I did computer science, I learned about the shortest path first algorithm. Why don't we try that? And so open just means it's open, it's usable by anyone. And so that's what OSPF is. It's built on that. And ISIS uses the same algorithm to calculate routes, just has slightly different mechanisms on how it exchanges information and how it classifies information. Okay, so Dijkstra's algorithm, and all link state routing protocols apply Dijkstra's algorithm, also known as shortest path first, to calculate the best route. The user's accumulated cost along each path from source to destination. Each router determines its own cost to each destination in the topology. The table displays the shortest path and the accumulated cost to reach the identified destination networks from the perspective of R4 in this case, because so basically this is what we're basing on. So of course all the routers have the same database because the network is the same as long as they've got up-to-date information. But of course each router needs to figure out the best path to each destination from where it is, not from where other people are. So that's why we're talking about from the perspective of R4 in this instance. And so R1's LAN is the cost of 17, R2's LAN is a cost of 22, R3's LAN is a cost of 12, and R5's LAN is also a cost of 12. And so, as you can see, you can if you run the sums through your head yourself, you can actually see which way that will go. Okay, so the link state routing process, how does it work? Each router learns about each of its own directly connected networks. Each router says hello, so they use a hello protocol. That's where EIGRP sort of borrowed that concept from. Each router builds a link state packet containing the state of each directly connected link. So a link state packet, of course, is a layer 3 packet. Within it, there are probably multiple link state advertisements within it. And so information about each of its connected networks. Each router uses the database to construct a complete map of the topology and computes the best path to each destination network. OSPF for version 4 or version 6 of IP works exactly the same way. It's just the addressing is different. That's the only difference between the two. So the first step in a link state routing process is that each router learns its own directly connected networks, much the same as all other routing protocols. Again, from the configuration, the interface is up, it's got an IP address, well, that's the network for that LAN. And then basically the routers, if they are configured to use a particular interface, they will send hello packets out of that. And so that's how the routers learn who their neighbors are. And so basically from there, each router will send hello packets, and so they'll each learn about each other, and so they can they'll again, of course, later exchange their link state advertisements, and they'll know what networks are connected to each of their neighboring routers. When two link state routers learn that of each other, they form an adjacency. If a router stops receiving hello packets from a neighbor, that neighbor is considered unreachable, and that's when we start recalculating what destination networks we can get to. So the link state packet is basically the third step, and so it adds the information for all the directly connected networks. And so R1's link state packet would include information about the 4 links that are directly connected to it. And so it's an Ethernet network plus the links to R2, R3, and R4. Then it will flood that link state packet to its neighbors. And so only an LSP only needs to be sent during initial startup or when there is a change. And so an LSP also includes sequence numbers and aging information used by each router to determine if it has already received that link state packet, and of course, is this the newest information. Okay, once they start receiving link state packets, they will update and add entries to their databases, and so they get a full picture of the network. And then once they will normally actually pause after receiving link state packets, just so that they can be sure that there are no more coming, because while very good at creating routes, the shortest path first algorithm is a fair bit of work, and so they just sort of delay to make sure that they're doing the SPF algorithm as few times as possible, basically. And so once they've waited and the link state packets have stopped arriving, then they will actually use the SPF algorithm to construct a tree. And so basically they'll then know what network connects which routers and so on and so forth. And so from there they can create the shortest path to which destination network it knows of, and then of course it can update the routing table. And so all the LSPs and everything, that's all a combined effort, that they all know each other's information, but of course the SPF algorithm, as we said before, is done from the perspective of each individual router, because they're all in a different part of the network. And so, as I said, once they've calculated the best routes to each destination, that's when they start updating the routing table with these new paths to the new destinations. Okay, so what's the benefits of a link state routing protocol? And so each router builds its own topological map of the network to determine the shortest path. Immediate flooding of LSPs achieves faster convergence. They're only sent when they're needed. And so basically, again, much like EIGRP, hello packets are normally the only packets that are going. And as I said, because you can create multiple areas, you can actually have a hierarchical design, and it makes things a lot more efficient. Disadvantages. So they use more memory, they use more processing, and bandwidth can be used when the networks are changing. And so that's actually another reason why you would define multiple areas, so that if you had this all in one area, all of these routers would have to know about all the other routers. And so within an area, they only have to know about other routers in their own area. And so it makes the traffic a lot more efficient, and also the routing tables a lot more stable. So, as I said, there's OSPF, of course, is version 2, which is for IP version 4, and there's version 3, which is for IP version 6. They're exactly the same routing protocol, again, just designed for the different addressing schemes. ISIS, of course, is used as well, and it's actually called dual ISIS for IP, because it was actually designed for CLNS, connectionless network system, which was developed by the ISO, but they've modified it to also use IPv4 and IPv6, and so That's why they call it dual. So we've come to the end of the chapter. And so we've spoken about the features of dynamic routing protocols in general, and then we've spoken specifically about distance vector and link state routing protocols and how they operate. There's the logo. So the video is finished. I'll see you next week at the lecture. Have a nice week.